Hello everyone. Today I'm presenting the paper AI-based condition monitoring of hydraulic valves in zonal hydraulics using simulated electric motor signals by Abid Azeez, Suhan, Viacheslav Zakharov, and Tatiana Minav. The content of this presentation includes background, methodology, results and discussion, conclusion and future development. Heavy-duty mobile machinery can be found in various industries such as construction, agriculture, forestry, and mining. The electrification of these machines is of significance in order to reduce air emissions as well as to save fuel costs. Zonal hydraulics, also known as direct-driven hydraulics, is an emerging transmission and actuation technique that is proposed for the electrification of mobile machinery. Its advantages include higher efficiency, compactness, ease of maintenance, and condition monitoring. Condition monitoring generally involves the use of a large number of sensors that are themselves prone to errors. However, in this paper, we are proposing an AI-based condition monitoring system that is capable of using electrical simulated signals rather than depending on a large number of sensors. A simulation model is developed and it consists of a hydraulic model, which is the check valve model, and an electrical drive model, which is the field-oriented control model. The data that is generated from these models is then fed to a preliminary classifier that is capable of fault classification. We will now take a look at the model under study. The schematics of two-pump direct-driven hydraulic model is shown here. Number one is the hydraulic cylinder. Number two, the electronics involved. Number three is the electric motor. Number four is the piston side pump. Number five, the rod side pump. Number six, a hydraulic accumulator. Seven are check valves, and eight are pressure relief valves. In this paper, faults are injected into the rod side check valve. The check valve model is shown here. It consists of the orifice flow model with nonlinear flow, orifice geometry model with variable minimum opening, internal volume model, ball motion model with variable friction force, and the fluid property model. Structure of the field-oriented control can be seen here. It consists of PMSM, permanent magnet synchronous machine, and the three-phase is converted to two-phase using geometric projections in order to simplify the control of the system. Two PI controllers are present for electromagnetic flux and torque, and another PI controller is for the speed of the system. There are a total of 16 fault cases that are simulated. The fault types include deadband, leakage, friction, spring, stiction, and the healthy case. Each of the fault types have three different levels of faults, and they're labeled as fault level 1, fault level 2, and fault level 3. The model analysis is performed by taking a look at the total harmonics distortion. The normal valve has a value of 5.585, and this is taken as a reference value. And we can see that the faults are having an increase in this value or a decrease. And there was one fault with unpredictable behavior, which is the dead band fault. Here we have the general condition monitoring steps. The first step is raw data, which is normally collected using sensors. However, in this research, we are using electric signals that are simulated. The next step is data preprocessing, where data could contain some noise and we need to remove this noise. This normally happens with the sensor data. Data scarcity, in case we don't have sufficient data, we need to do some kind of data augmentation. And feature selection, we build a correlation matrix in order to check whether the feature that we are going to consider is really required or not. The next step is to choose an algorithm. So this is a machine learning or artificial intelligence based algorithm, which is going to be the classifier. We need to then train this classifier with a certain percentage of available data. The normal norm is to use 70% for training and the remaining for testing and validation. The next step is to evaluate the classifier, which is using the remaining data that we had separated. And finally, we have the fault classifier, which is the final algorithm that's capable of fault classification. Correlation matrix is used for data pre-processing. Here we can see the various variables: mref, which is the motor pump speed reference; mres, motor pump speed response; u, v, and w, current responses of the three phases of the motor; piston side pressure, rod side pressure, and hydraulic accumulator pressure. Now, for machine learning, we need certain features, and these are considered as the features that are available from the data that we have. However, we do not want to use all the features in case some share some correlation between each other. So in this case, I have drawn a square block here. Diagonally, we can see that all are correlated, and we can see that mref and mres are correlated, so we can discard one of these features while performing the algorithm training. Several machine learning algorithms are selected. The models are evaluated based on precision, recall, F1 score, and accuracy. Here we can see the sample classification report, and I'm bringing back table 1 to have a reference for the labels. So 0 to 15 are labeled here, and in parentheses we can see what these are. So for example, dead band fault level 2 is labeled as 1 and healthy case is labeled as 3. Taking a look at the precision column, we can see that it is almost 100% accurate in predicting faults 0, 1, 2 as well as faults 10 to 15, and it is weak in predicting faults 3 to 9. Several algorithms are tested upon training and the accuracy score is obtained for them, and we can see that the highest accuracy score is for multi-layer perceptron, which is 70% accurate, while the least performing is the k nearest neighbors with a 30% accuracy score. Here we have a figure that shows the multi-layer perceptron classifier architecture. It consists of an input layer, few hidden layers, and an output layer. The confusion matrix for the multi-layer perceptron classifier is shown here. We can follow the green box. Diagonally, we are supposed to have white boxes throughout the confusion matrix. However, we can observe this red rectangular area that does not have this particular white colored boxes. The labels that have this issue are from 3 to 9. And taking a look at the table, these are the leakage fault, friction fault, and the healthy fault. So the classifier is basically confused between these three types of faults and misclassifies them. In conclusion, the preliminary artificial intelligence-based condition monitoring classifier for valve was developed using the simulation data. The MLP classifier was found to be the best classifier and was able to achieve an accuracy score of 70% for all the 16 different fault cases. In this paper, only a single type of fault is introduced in each simulation run, and this is used for training the classifier. However, faults can coexist, and this can also lead to misclassification. The next direction would be to simulate faults in other components of the hydraulic system and develop a robust condition monitoring algorithm for fault detection in DDH system.